Very welcome. You are coming to a laboratory of supersonic flow and combustion control. My name is Sergey Leonov. I am in charge of this laboratory. This, to some extent, it's a very unique laboratory because, let's say, it's an all-in-one. We are dealing with supersonic, hypersonics, advanced diagnostics, and many other things like material testing and combustion. So you are welcome to our laboratory. I will show you two different facilities. Basically, it's complementary facilities. One is on my left side. It's a SBR50. It means a supersonic blowdown test rig. 50 is just a cross section of a test section. And another one is the Notre Arc-Jet facility on my right side. Welcome. This one is a unique supersonic facility. It was originally designed for experimentation with a supersonic combustion. Supersonic combustion makes sense for hypersonic flights, for scramjet or dual mode engines. It's a propulsion for hypersonic vehicles. As normally for many supersonic facilities, we have a high pressure side right there, and low pressure side. This big guy, this tank, is a low pressure. It's a vacuum, really low pressure. So initially, that tank is charged with a high pressure air or any other gas. Then some portion of this gas coming to a plenum section. Plenum section is what is unique here. That's that one, because we have electrical heaters installed inside. Electrical heaters which allows us to heat air up to 800 Kelvin. I am confused to how to. It's about should be 1,200 Fahrenheit, something like this. So then this air, when we need this, we open gate valve, and this air going very fast. It's let's say about 500 miles per second velocity. This air going to a low pressure side there, which then pump it out outside. So what is the uniqueness of this facility? Normally, in general, we heat it for several minutes and then release for a couple seconds. It means that we have power several megawatts in a laboratory at laboratory conditions. Run itself, duration of run itself, it's just 1 second. Very short. When we open gate valve, the rarefaction wave coming to a plenum section and going down here. To compensate this rarefaction wave, which is actually leads to a cooling of air and drop down the pressure inside, we open set of these valves with a spider on the back side. When we open this one, we generate compression wave which compress air inside and allows us to keep pressure and temperature on a high enough level. Facility itself is nothing without proper diagnostic. Diagnostic here includes some conventional methods like a pressure measurement, temperature measurements, and some advanced diagnostics. Later on, I will ask my student to talk a little bit more about advanced diagnostics. Some diagnostics, you can see some diagnosis outside of this facility. could be controlled by one single person just by pushing one button, and everything will proceed automatically. Right now we will go to another facility. Another facility is call it right now Notre Arc Jet facility. Was originally designed for a re-entry problem. Re-entry, I believe everyone knows what is re-entry is. It's when a spacecraft coming back to Earth and in upper atmosphere it's experienced with a really high thermal and thermal loads and some forces. But then it was redesigned to make a more flexibility, and right now it's an all-in-one facility in terms of a hypersonic. So it's a Mach number 6, or we can even think about high Mach number and very high enthalpy of the flow. Let's say temperature could be as high as 6,000 Kelvin. Here, let's look at more details. So here is a test section, and there on a SBR50 test section is a closed test section with a parallel optical windows to have a good optical access for a model tested and for combustion problems. But here is an open test section when we have a nozzle right here. So it means that we will have a jet. The jet duration is also several seconds, and then it's difficult to see right now, but you can maybe to show something there. It's a model installed. It's a small model which in this particular case is installed for material testing at high enthalpy flow. It will be preheated with a very powerful laser and then exported with a hypersonic flow from this facility. It's a little bit smaller facility, lower density, but much higher enthalpy of the flow. Really hypersonic flow field. Everything was renewed very recently, and now it's in a good this facility in a good conditions. As I said before, we have several advanced diagnostics here. When I talk advanced, I mean laser diagnostics. Before I will ask Philippe to say a little bit more about advanced diagnostic, I would emphasize that we are dealing here with a high pressure, high velocity, high temperature, high voltage. I forgot to say that we are dealing with the plasma as well here. What is it? Another high. Everything is really high. So after getting the skills from this laboratory, you can have in your CV something like hypersonics, supersonics, combustion, scramjet, plasma, and lasers. And right now, let's go there. Can you please talk a little bit about laser diagnostics? Sure.
So this is one of our new laser systems. This is a CORS system, a clearance anti-stope non-scattering system. It's partially disassembled now because I'm setting up a CO2 scattering system. But I'm going to walk you through the laser system briefly. So this is a 10 hertz nanosecond pulse laser. Pulse energy is about a joule. So on a 10 nanosecond pulse, the instantaneous energy is on the order of 100 megawatts. So it's being frequency doubled and frequency tripled to from the fundamental frequency of 1064 nanometers to 532 nanometers and 255 nanometers. And the third harmonic, which is in the UV, is coming and pumping this OPO, optical parametric oscillator, which is basically doing frequency difference generation. So it's taking a high energy UV photon and splitting it into two. one at 6 or 7 nanometers and one at 855 nanometers, which is in the IR. The orange light at 6 or 7 nanometers is then being sent up to the test section where it's joined by the 532 nanometer light, which is green. The green and the orange light overlap using a dichroic mirror. The green light is reflected and the orange light is transmitted. They're being focused into the test section, and at the focal point of those two beams, the call signal is being generated. The difference in frequency of orange and green light corresponds to the relative vibration of molecular nitrogen, and that call signal is being generated and is being sent into the after-unit spectrometer. So with this method, we can measure vibrational temperature and rotational temperature of nitrogen, and we're interested in looking at the vibrational temperature of non-equilibrium flow. So flow have high vibrational temperature, but simultaneously very low static temperature.
Thank you, Philip. Briefly, that's all. If you have any questions, you can just send me email and we will set up appointment and you can come and get more details about our laboratory. So welcome to Notre Dame.